When doing our tests for significance, we'd like to know like how small of a p-value is small enough to say that we've found strong evidence. And this comes to the idea of statistical significance. And this is generally what's called a level of significance, and it's determined at the beginning of a study before any data has been collected. We decide what level of significance is our threshold. Okay, we call this number alpha. Okay, if the p-value is as small or smaller than alpha, we say that the data are statistically significant at level alpha. Okay, this quantity alpha is called the significance level or the level of significance. So let's look at an example, and this is an example that we've already looked at. We had a sample of 250 students that had a mean GMAT score of 542. Remember that the mean, the actual mean for the whole population, was 550. Okay, and we wanted to know if this mean was lower. So our null hypothesis was that the mean equals 550, and the alternative hypothesis, we were looking for evidence that the mean was less than that. Okay? And so what we do we compute, of course, our test statistic. So our test statistic here is our z-score, which is 542 minus 550 over the standard deviation. If you remember, the standard deviation was 120 over the square root of the sample size 250. Okay, this was a previous example that we had. And this came out to be about negative 2.37. Okay, so looking at kind of a picture of our normal distribution, okay, for our test statistic of z, of course, our mean would be 0 for a standard normal distribution. And we found this negative 2.37, or if you do it in terms of the raw data, the raw numbers, then you've had a peak at 550, and we found, of course, over 542. So we got this number over here, and because this is a one-sided hypothesis, we just care about that extreme on that far left. So we just want the area to the left of that negative 2.37. Okay? So our p-value is going to be the area to the left of that z value. So we can go ahead and compute that in Excel. We've got a normal distribution, and it's standardized. And we're looking for the area to the left of negative 2.37. Okay, and we've got to do that cumulative. Okay, and we get 0.00889. 0.00889. Is this outcome statistically significant at the alpha equals 0.05 level? So all we check is if this is less than that alpha. Well, yes, this is less than 0.05. So yes, it's statistically significant at that level. Is it statistically at the alpha equals 0.01 level? Well, yes, it's also less than 0.01. And so it's also statistically significant at that level. It is not, however, statistically significant at the, say, alpha equals 0.005 level, because it's not less than 0.005. Let's look at another example, one that we haven't seen yet. The National Center for Health Statistics reports that the systolic blood pressure for males 50 to 59 years of age has a mean 130 and standard deviation 15. The medical director of a large company looks at the medical records of 72 executives in this age group and finds that the mean systolic blood pressure in this sample is X bar equals 128.07. Is this evidence that the company's executives have a different mean systolic blood pressure from the general population? For these problems, when we're looking for this evidence, okay, we are always going to set up our hypotheses first. So we have our null hypothesis and our alternative hypothesis. We're looking at the mean blood pressures, okay? And so we're talking about mu. So mu equals, and we know that the mean, okay, the National Center of Health Statistics reports this mean at 130. So we know it's 130. And we're looking for evidence that the company executives have a different mean systolic blood pressure. So we're looking for evidence that mu is different, so not equal to 130. Doesn't matter which side. We'll look on both sides. That's what we're looking for evidence for. Next, we'd like to just draw a picture of what it is that we're looking at. Okay, we're going to have a normal distribution. It doesn't matter how blunt your picture is. Okay, we've got our peak at 130, okay, and we have this value of 128.07. I don't know where it is. I don't really care about where I draw it, but it's over here to the left. And because I'm looking at different than, not equal to, we look at both sides. So we're actually going to look at, however extreme that is, we're going to look at the areas on both sides and find out what that area is. So I like to keep that picture in my mind from the very beginning so that I remember what it is I'm looking for. The next thing is just state what the actual distribution is. We've got a normal distribution. The mean is 130, and the standard deviation should be the standard deviation of the population, 15, over the square root of the sample size. And the sample size here is 72. Okay, so now we compute our test statistic for the data that we've collected. Our test statistic is Z. Okay, and that is that test statistic is telling us how far away our data is from what we'd expect under the assumptions of the null hypothesis. So we take our 128.07 minus the mean of 130, divide by the standard deviation, 15 over root 72. Let's go ahead and plug this into Excel. So we have equals 128 minus, 0.07 minus 130 divided by 15 over the square root of 72. Okay, we get negative 1.09 approximately, negative 1.09. Okay, that's the Z value right there. So now I know I can get the area to the left of that and then just multiply it by 2. So to get that, I can do that in Excel. This is a normal distribution that's been standardized. So norm.s.dist of that Z score that I just got, comma 1 for cumulative. That is the area to the left. And I take that and I multiply it by 2. So 2 times that. And I get 0.275. That's my p-value. 0.275. All right. Obviously, this is weak. This is not evidence at all. This is not a low level. Generally, our alpha, of course, is around a 0.05 or 0.1 or 0.01. Okay, those are our common values for alpha. So no, this is not evidence that the company's executives have a different mean systolic blood pressure from the general population. Sulfur compounds cause off odors in wine. So winemakers want to know the odor threshold, the lowest concentration of a compound that the human nose can detect. The odor threshold for dimethyl sulfide in trained wine tasters is about 25 micrograms per liter of wine. The untrained noses of consumers may be less sensitive, however. Here are the dimethyl sulfide odor thresholds for 10 untrained students. Assume that the odor threshold for untrained noses is normally distributed with standard deviation of 7. And we'd like to know, is there evidence that the mean threshold for untrained testers is greater than the 25 micrograms per liter of trained wine testers? So we'd like to know if we've got evidence. We should probably determine a threshold here. So I'm going to pick my alpha level of significance to be 0.05. And I'm going to find out if it's significant at that level. So the very first thing I want to do is just state my hypotheses. Okay, my null hypothesis is that I'm talking about untrained tasters, and the mean, well, that I'm kind of comparing against is the 25. So I want to know if that's equal to 25. That's going to be kind of my assumption. And then we're looking for evidence specifically that the mean is greater than that. So that mu is greater than the 25 micrograms per liter. So there's my hypothesis, my statements of my hypotheses. Looking at what that means, we're talking about, that's not the best. We've got a normal distribution, okay, and our mean is at 25. And we're saying, well, if I find some value, I'm looking for a value that's greater, and then I want to know whatever I get, I'm going to look at the area to the right of that. Okay. Then we'll write the distribution. We have a normal distribution with a mean of 25. And our standard deviation for the sampling distribution is the population standard deviation over the square root of the sample size. And our sample size here, we've got 10 numbers there. All right, so we've got these numbers here, and we need to go ahead and get our statistic from that. So our X bar, the mean for those 10 students. So I've got that data here in Excel, and we'll go ahead and compute the average for those numbers. We get 29.4. 29.4. That's our X bar. Okay. So obviously that's bigger than 25, but we'd like to know, is that a surprising result in a sample of size 10 or not if the mean for the general population was still 25? So we compute our test statistic Z. We take our mean, 29.4, and subtract the population mean, the 25 that we're comparing against. Divide by the standard deviation, 7 over the square root of 10. And we'll go ahead and compute that here in Excel. So equals 29.4 minus 25 divided by 7 over the square root of 10. And we get about 1.99. Okay, about 1.9. And so that's this value over here in the standardized normal distribution, and we're looking for the area to the right of that. And so that's going to be our p-value. Okay, so that's going to be, we've got a standardized normal distribution. And for that value right there. And this is, of course, going to give us the area to the left of that, but I want to the right. So I'm going to do 1 minus that. And that gives me the p-value of 0.023. And this is less than alpha, which I set at 0.05 at the beginning. And because it's less than alpha, I have found strong evidence that the mean threshold for untrained testers is greater than the 25 micrograms per liter. Okay, now that's evidence that's statistically significant at the alpha equals 0.05 level of significance. Okay. If I had chosen a smaller level, for example, if I had if I had chosen 0.01, okay, this is not less than that. So it's not statistically significant at the alpha equals 0.01 level of significance.